So one of the big concepts that's involved in plate motion is convection currents. So what is convection? Convection is the transfer of thermal energy, or heat, in other words, by the movement of heated materials. You basically have three ways that heat is transferred. You have convection, which is actually movement of materials, like hot air rises, for example. That's convection. Warm water rises. That's convection. Cold water sinks. That's also part of convection. But cooling of matter causes it to condense, which increases the density. Cooler matter then sinks due to gravity. Warmer matter then is displaced and forced to rise. Notice I'm just saying matter here. It could be water, it could be air, it could be magma in the mantle, right? And particularly, we're talking about magma in the mantle and those convection currents that cause plate motion. But this results in a convection current, where the example here, you have an ice cube at the top of the beaker and you're heating it basically on one side here. If you put some food coloring in there, it's basically going to sink. It's going to get cold here at the top where the ice is. It's going to sink to the bottom. And as it sinks, it's going to basically start moving across the bottom and push this less dense warm water up. And eventually you get this whole little pattern here, this little circular pattern, which as long as, until the dye completely distributes in here, you can kind of just watch it kind of circling around. Lava lamps work like this. You have the sort of wax at the bottom, you heat it up, it rises to the top, it cools, and it sinks. And then it'll heat back up at the bottom, it rises to the top, it'll cool, and it'll sink. So lava lamps work on this same principle. But that is also the same thing, one of the things that causes tectonic plates to move. All right, so convection in the mantle. So Earth's mantle is primarily made of solid material that is heated unevenly by radioactive decay from the mantle itself and the core beneath it. So you got some radioactive decay that's heating it, you've got heat from the core that's heating it, etc. But this causes solid rock to slowly flow like a soft, pliable plastic. So it's still solid, but it's like, it's a softened solid, I guess is a way to think about it. It's not a rigid solid anymore. It's sort of a soft, kind of gooey solid is a way to think about it. But then part of the mantle is too cold to flow, and that's attached to tectonic plates. As mantle material cools, it slowly sinks toward the center of the Earth. Emphasis on slowly. Causing heated material to be displaced and rise. So you got the heated material that is, let's do it this way. You got the cooling material that is sinking, and then that will start to push the heated material that's less dense up. And we'll see here in a minute, eventually it kind of hits the bottom of the crust. Actually hits this part of the mantle that can't flow, that's attached to the bottom of the plate. So eventually this heated material comes up, hits that, and once it hits it, it's got to go somewhere, so it kind of hits it and then spreads out to the sides. Okay. But anyway, these currents then flow at rates of only a few centimeters per year. Like I said, emphasis on slowly sinks. So then plate movement, so the rising material in the convection currents spreads out as it reaches the upper mantle, because again, it has nowhere to go. So once it rises up here, it eventually hits solid tectonic plate pretty much, and it has to sort of mushroom out to the sides. And when it does that, it kind of starts to drag these plates along with it. So this creates an upward force because you got the material rising, and also a sideways force when it kind of hits that and starts to spread out. These forces lift and split the lithosphere at divergent boundaries. So right here, the divergent boundary, which is this is the mid-ocean ridge, this material is rising up. It's kind of pushing this up, and it's also kind of spreading out the side. So it's got this sort of kind of putting a force upward and outward at the same time, and that kind of basically splits and pulls this apart. The downward part of the convection current, because there is the other side to this, you got the downward side of this as well over here. But that occurs where a sinking force pulls tectonic plates downward at convergent boundaries. So you have the upward force here that's kind of pushing them apart here. And then that whole thing is acting like a little conveyor belt. Just that magma is kind of going up, it's going across, and then it's going down. As it's going down, it is able to put some pressure on this and start to pull this down as well. So you kind of got it acting on both ends of the plate. So you got pressure kind of up and out here, and then down and well, it's still kind of out, I guess, but basically you got a downward force here that's kind of pulling this back down into the mantle. All right, so ridge push and slab pull. So oceanic crust becomes denser and sinks as it cools and moves away from the divergent boundary. And basically, ridge push occurs as the older, denser portion of the seafloor sinks, and the weight of the uplifted, less dense ridge pushes the oceanic plate toward the trench formed at the subduction zone. Okay, so in other words, what you've got here is if you have your ridge like this, I'm going to draw this on over into a trench here. So say a trench there, and your ridge kind of coming off this way. The ridge push is happening because you got material that's basically coming up here. Your magma's coming up. It cools. As it cools, it keeps adding weight to the top of this, which then starts to push down on that plate and push it away from that ridge. This is happening on both sides. So you have the ridge push is basically the material that's being added at the top of that ridge that just keeps adding weight to it and keeps pushing it down. And then slab pull is where the weight of the relatively cool, dense subducting plate pulls the trailing slab into the subduction zone, much like a tablecloth slipping off the table can pull articles off with it, or like a sheet of paper. If you have a sheet of paper laying there and you set something on it and you pull the sheet of paper off the table, whatever you've got sitting on that paper is going to be drug along with it, because this whole thing is connected. So this part here starts to sink. Well, that's going to basically pull on the rest of it that's attached here and pull on the rest of it. And then you got your ridge push adding to that. Effectively, that whole process causes this plate to move. Add one more thing to that, if you think about your convection currents down here. So the combination of those three things, the convection currents, the ridge push, and the slab pull, are all contributing to making these plates move. It's likely that the slab pull is more important than the ridge push in this. So this is just that slab pull, ridge push sort of in diagram form. First off, you got to remember you do have your convection currents that are kind of coming up towards the ridge and then moving out to the sides here. The material that builds up on that ridge is basically going to push down and away from that ridge, which kind of is giving you a force on the front part of that plate, kind of pushing it away from the ridge. The convection and the mantle here is going to kind of give it some extra force in the middle, kind of moving it along. And then you got the slab pull at the other end of it that's kind of pulling it back into the mantle and melting it. So